Welcome to the class on artificial neural networks. This video gives a first learning algorithm called the Perceptron algorithm. Remember that the simple perceptron implements a hyperplane at a certain distance from the origin. Now, if we go to n+1 dimensions, which means if the threshold parameter is integrated as an extra input parameter, then the hyperplane actually goes through the origin. Now let's look at this situation here. All the green samples should lie on the same side as the pointing direction of the weight vector. So this one here is correctly classified, this is as well, this as well. However, this one is not. Now the reason is that the hyperplane, the dashed line, doesn't have the right orientation. So let's turn it and suddenly it's perfect. This is now okay, and the other problematic point on the left hand side, which was this one, has also changed. So it's also okay. So if a problem is linearly separable, then somehow we should turn the hyperplane such that in the end the hyperplane nicely separates the positive examples, the green crosses, from the negative examples, the red circles. So the idea is a learning algorithm should turn the weight vector. And here is the algorithm. So we have many patterns. You choose one of the patterns. For example, pattern number 1 as a first pattern. Then for this pattern mu, you calculate the output, and the output is just this nonlinear transform, this step function. And note that there is no threshold because we are in n+1 dimensions. And then we update, we change the weight vector in direction of the pattern that we have tested, but we change it proportional to this factor here. And now in this factor, you compare the target output with the actual output. So if the actual output is a 1 and the target is a 1, then no change happens. But if the target is a 1 and y hat is 0, then we change, and we change in direction of this input pattern. So let me explain this algorithm. Let us pick two axes. So this is input dimension x1 and is some other input dimension, say x17. And now let me draw the weight vector, the current position of the weight vector, and it's maybe like this, and I will draw the hyperplane that is perpendicular to the weight vector. So this is the weight vector, it's not normalized, and then the hyperplane goes through the origin because we are in n+1 dimension, so there is no threshold here. The threshold is integrated in as this extra dimension. Now suppose we have a couple of data points. I have a data point here, that would be wrong, and then I have a couple of data points that are already correctly classified, and then I have a couple of negative data points like these ones lying here and there, and maybe there's also a negative one which is misclassified. And now what does the algorithm do? So here we have, if I add another one, we have 10 data points, 5 positive ones, the green crosses, 5 negative ones. And now we cycle through these data points. For example, we take this one here. It's correctly classified. It's a positive data point, and it lies on the side in which the weight vector points. Then let's take this one. It's a positive data point. It's also correctly classified. This one is correctly classified. Let's look at one of the negative ones, well, this one is also correctly classified. This one is also correctly classified because they lie on the other side of the hyperplane. And then we look at this one here. This one is misclassified. So let's look at this misclassified data point. It's a green cross. That means the target value is +1. And it's on the wrong side of the hyperplane. So the actual output is 0. And now I have a learning rate, gamma, which is arbitrary in this algorithm. In most algorithms, the size is important. Here it's not. So let's set the learning rate equal to 0.1. And then what does this algorithm mean? Okay, I have 0.1, just as an example. And then I have 1 minus 0. So it's 0.1 times x. What was x? X is the vector of the data point that is misclassified. And so now I make a small change of the weight vector, delta W, which is in direction of x with this prefactor gamma. And then what's the new direction of the weight vector? The new direction of the weight vector would be this. And that means the new hyperplane going through the origin is this one here. And I've solved the problem. So the problem was constructed here such that it turns the right amount with a single application of the pattern. In general, that's not true. If I had taken gamma equal 0.0001, then it would turn only a tiny little bit. So in the first round, it would not turn enough. If I had taken a gamma that's 0.5, it would have turned a little bit too much, and I would have to turn back later. But if I cycle through all patterns several times, at some point it will converge. And the reason is that across many iterations, the length of the weight vector, this length gets longer and longer, so that the relative importance of the update, which is always of size gamma in some sense, becomes smaller and smaller. No, so what I just said is that this algorithm converges, and there's a condition for this. If the problem is linearly separable, that means if there's a hyperplane that can separate the positive examples from the negative ones, then the algorithm converges, and moreover it does so in a finite number of steps. And this is a really, really classic result. The proof is in many books, and later in the exercises you will construct a different proof, not the standard textbook proof, a proof that points to loss functions and gradient descent. That's topics that we will say later. So let me summarize. The Perceptron algorithm can solve linearly separable problems. To do that, you have to cycle several times through all patterns until nothing changes during a full cycle. The update is always proportional to the weight vector. Now, I say proportional. In fact, it's in direction. So plus that delta W is positive in direction of x mu if I have a positive example, and it's anti-parallel if I have one of the negative examples that are mismatched. The proof shows the initial value of the weight vector is not important. The learning rate is not important. The reason is the length of the weight vector W grows. And in the end, for these classifications, only the direction matters. Before we finish, let's do a little quiz. I walk you through in 2 steps. Let's first read together the first set of 2 questions, these 2 here. We assume here that the input vector has n dimensions. That's very important for the answers. And we apply a Perceptron algorithm. The claim is a change of parameters corresponds always to a rotation of the separating hyperplane in n dimensions. And second question, a change of separating hyperplane implies a rotation of the hyperplane in n+1 dimensions. So think about it for a moment, pause the video. And here's the answer. It's in n+1 dimension that you can describe the changes as a rotation of the hyperplane. Now let's look at the second block of questions. And in the following, I mean a change that does not change the direction. It just makes the weight vector longer or shorter. And so in this setting, you do an update that changes the length of the weight vector. The first claim is an increase of the length of the weight vector implies an increase of the distance of the hyperplane from the origin in n dimensions. Second, an increase of the length of the weight vector implies that the hyperplane does not change in n dimensions. Third, an increase of the length of the weight vector implies that the hyperplane does not change in n+1 dimensions. So think about it for a moment, pause the video. And here's the answer. Only the third one is correct. So if you are in n+1 dimensions, then the length of the weight vector doesn't matter. However, in n dimensions, it does matter because it changes the distance from the origin, but the distance does not increase, but it decreases, as you see from the construction of the hyperplane.